Somewhere in a laboratory in Boulder, Colorado, in the year 2010, a group of scientists did something that sounds almost too small to matter. They took a clock. Not a clock like the one on your wall, and not a clock like the one glowing quietly on the phone beside your bed. This was a different kind of clock, one that keeps time by listening to the trembling of a single kind of atom. And they took this clock and they lifted it up. Not far, about 33 centimeters, roughly the height of a single step. The height of a curb at the edge of a road, the distance from the floor to the seat of a low chair. That much, and no more. And when they lifted it, the clock began to run faster. Not because they jostled it, not because they knocked something loose inside. It ran faster because it was now very slightly further from the center of the Earth, a little higher out of the planet's gravity. And time, it turns out, runs at a slightly different speed depending on how deep you are inside gravity's pull. Lower down, where the pull is stronger, time runs a touch slower. Higher up, where the pull is gentler, time runs a touch faster. This is not a metaphor. It is not a trick of the machine. It is the way the universe is actually built. And for the whole of human history, it was invisible to us, hidden far below the level of anything we could measure. Until, one afternoon, a clock got good enough to feel the difference across the height of a single step. That is where we are going tonight, slowly, gently, all the way there and all the way back to the beginning, to see how we ever built a thing so sensitive that it can taste the height of a curb. But before any of that, let me simply say, welcome to the Curious Voyager. It is lovely to have you here. Wherever you are right now, whatever corner of the world you have carried this little voice into, I'm glad you came. Maybe you're lying in a dark room with the blankets pulled up and one lamp still burning low in the corner. Maybe you're on a train, watching the lights slide by. Maybe it's the middle of the night and the house has gone quiet around you, and this is the only sound left awake. Wherever you are, and whatever time it is in your part of the night, settle in. You don't have to go anywhere. You don't have to do anything at all. And if you're enjoying these slow journeys, and you'd like more of them to drift off to, a gentle like and a subscribe really does help this sleepy little channel keep going. Small channels like this, one lean on that more than you'd think. And I'm grateful for every bit of it. To those of you already here, already part of this quiet little crew of night travelers, thank you. Truly, and I'd love to know if you feel like leaving a small note before you fade off. Where in the world are you listening from tonight? And what time is it in your corner of things? It's a nice thing to imagine all of us scattered across the dark, listening to the same story. Now, here is my usual promise and my usual warning, which come as a pair. I'm going to try very hard not to make this so interesting that it keeps you awake. That's the goal. We're going to move slowly, one idea at a time, the way you'd wander down a familiar road with no particular need to arrive. There's no test at the end. There is nothing you need to hold on to. If your eyes are already heavy, let them close. If you drift off somewhere in the middle, that is not a failure. That is exactly what this is for. The ideas will still be here. The clock has been ticking for a very long time, and it will keep ticking whether you're awake to hear it or not. You can come back to any of it another night. So there's no need to concentrate, no need to remember, no need to understand every piece. Just let the words move past you like the countryside past a window. And I'll admit, some of what we talk about tonight is genuinely strange. The nature of time usually is. But I'll do my best to keep it soft. If some part of it does snag your attention and keep you up a little longer than you meant, well, At least you'll have learned something lovely for the trouble. A fair trade, I think. So, let's begin, shall we? And let's begin not with atoms, not with lasers, not with satellites, but with the simplest possible question, the one hiding under all of this. What is a clock, really? Not what does a clock look like, not what shape is it, or what does it hang on, or whether it has hands or numbers, or a little glowing screen. What is a clock, underneath all of that? What is the actual thing? And the answer is smaller and stranger than you might expect. A clock is just two things put together. The first thing is something that repeats, something that does the same motion over and over and takes the same amount of time to do it each time. A swing, a tick, a pulse, anything that beats out a steady rhythm. And the second thing is a way to count those repeats. That's it. That is the whole secret. Something that repeats, and a counter to keep track. Put those two together and you have a clock. Everything else, the brass, the glass, the gears, the polished wood, is just decoration around those two simple ideas. Think about that for a moment, because it's worth sitting with. When you look at a clock and it tells you an hour has passed, what has really happened is that some little thing inside it has repeated its motion a certain number of times, and the clock has counted them up. The hands don't measure time directly. Nothing measures time directly. All a clock ever does is count how many times something has repeated and turn that number into hours and minutes for you. Time, in a sense, is just a tally, an accumulated count of small, patient, repeating events, which means the deepest part of any clock, the truly important part, is that repeating thing, the thing that beats. Physicists have a lovely plain word for it. They call it an oscillator. Don't let the word bother you. An oscillator is simply anything that swings back and forth, or vibrates, or cycles in a steady, regular way. A child on a swing is an oscillator. A weight bobbing on the end of a spring is an oscillator. Your own heartbeat, more or less, is an oscillator, though not a very reliable one. It speeds up when you're frightened and slows when you're calm, which is exactly what you don't want in a clock. The whole history we're going to wander through tonight. The entire long story from wooden pendulums to trembling atoms is really just the story of people searching for a better and better oscillator, a steadier beat, a more trustworthy tick. And there's one more idea I want to give you, gently, right at the start, because it's the quiet thread running through everything else. When you go looking for a good oscillator, what makes one better than another? Why is one swinging thing a better timekeeper than some other swinging thing? It comes down to how stubborn the thing is about its own rhythm. A good oscillator has a rhythm it really deeply prefers, and it does not like to be talked out of it. Nudge it, warm it, cool it, jostle it, and it keeps beating at very nearly the same rate anyway. A bad oscillator is easily persuaded. Its rhythm drifts with the temperature, or the weather, or its own age. It wanders, and a wandering beat makes a wandering clock. Scientists measure this stubbornness, this purity of rhythm, with something they call the Q factor. You don't need the mathematics of it, not tonight, not ever really. Just hold on to the feeling of the idea. A high Q factor means the oscillator is fiercely devoted to one single frequency, one exact rhythm, and resists anything that tries to shift it. A low Q factor means it's sloppy, easily pushed off its beat. Picture a fine wine glass, the thin crystal kind. Flick it with your fingernail, and it sings, one clear, pure note that hangs in the air and takes a long, long time to fade. That ringing purity, that unwillingness to let the note die or blur, that is a high Q factor. Now picture flicking a plastic cup instead. A dull little thunk, gone at once, no note to speak of. That's a low Q factor. And it turns out that the entire quest for a better clock, from the very first swinging pendulum right up to the atoms we'll meet later, is a quest for a purer and purer ring. A crystal note that hangs in the air longer and longer until finally we find a note so pure it barely fades at all. Hold on to that. The purer the ring, the better the clock. Everything else is detail. So, with those two little ideas tucked safely in your pocket, a clock is a repeating thing plus a counter, and the purer the repeat, the better. Let's go back. Let's go back a long way, to a time before any of this was understood, when the best clocks in the world were still shockingly bad. For most of human history, our clocks were, frankly, terrible. The very finest mechanical clocks that existed, the great tower clocks and the proudest devices any craftsman could build, might lose or gain 15 minutes in a single day. 15 minutes. Imagine that. You set your clock carefully at noon, and by noon the next day it might be a quarter of an hour wrong in either direction, and you'd have no way of knowing which. For most of ordinary life, this hardly mattered. If you lived by the sun and the seasons, if the important events of your day were sunrise and midday and dusk, then a clock that was a few minutes off was more than good enough. Nobody was scheduling anything to the second. The world simply didn't run that finely. But there were people for whom it mattered enormously. And we'll come to them soon, out on the open ocean, in real danger, with everything riding on knowing the time. For now, just hold the picture. For thousands of years, our best oscillator was a poor one, a dull thunk instead of a clear ring. And then, in the middle of the 17th century, a Dutchman changed everything with a swinging weight. His name was Christiaan Huygens, and in 1656 he designed and built the first working pendulum clock. Now, the idea underneath his invention had been noticed before, by others, in pieces, the curious fact that a swinging weight seems to keep remarkably good time. But Huygens was the one who turned that fact into a real working machine, and the improvement he achieved was not small. It was staggering. Overnight, more or less, the best clocks in the world went from losing about 15 minutes a day to losing only about 15 seconds a day. Sit with those two numbers for a moment, because the leap between them is the whole point. 15 minutes down to 15 seconds. A clock 60 times better than anything that had come before, arriving in a single stroke. That is one of the great sudden jumps in the entire history of measurement, and it happened because Huygens found a better oscillator, a purer ring. So what was so good about a pendulum? Why did a swinging weight keep such steady time? Here is the lovely thing about a pendulum, and it's worth going slowly over, because it's genuinely one of nature's small miracles. Take a weight, a bob, they call it, and hang it from a string or a rod so it can swing freely back and forth. Now here's the part that feels almost magical the first time you really understand it. The time it takes to complete one full swing, over there and back again, does not depend on how far you pull it. Pull it out a long way and let go, and it makes a big, wide, fast sweep. Pull it out only a little and let go, and it makes a small, gentle, slow sweep. And yet, both swings take the same amount of time. The big swing has further to travel, but it travels faster to cover that distance, and the small swing has less far to go, but ambles along more slowly, and somehow beautifully, the two effects cancel out almost exactly. Every swing takes the same time as every other. The pendulum keeps its own steady beat, no matter how hard or softly you push it. That is a genuinely good oscillator. A high Q factor, ringing away in the corner of a room, sweeping back and forth, each sweep a small identical repeat, and all a clockmaker had to do was build a set of gears to count those sweeps and turn them into moving hands. A repeating thing and a counter. That's all a pendulum clock is. A very good repeating thing, at last, and a clever mechanism to count it. And for the next 300 years or so, the pendulum reigned. It was the finest timekeeping oscillator humanity had, sitting in tall wooden cases in halls and observatories and studies, patiently sweeping out the seconds. If you close your eyes, you can probably hear one now, that slow, even, wooden tock, 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 the sound of a grandfather clock in a quiet house, a sound almost designed to make you sleepy. That sound is the sound of gravity and a hanging weight, agreeing on a rhythm, over and over through the night. But, and here is where our story takes its first real turn, the pendulum had a weakness, a deep one, a weakness built right into the heart of why it worked so well. And that weakness would send us searching for something better and eventually chase us all the way to the atom. So let's go slowly here, because this is the first crack in the machine. Think again about why the pendulum keeps time. It swings because of gravity. Gravity is the thing pulling the bob back down toward the bottom of its arc every time it rises, and it's the strength of that pull working on the length of the pendulum that sets the rhythm of the swing. And that is the trouble. The pendulum's beat depends utterly on gravity being steady and on the pendulum hanging quiet and undisturbed. Take away either of those, and the beautiful steadiness falls apart. So imagine now, taking a pendulum clock somewhere gravity is not steady underfoot, somewhere the whole world is heaving and rolling beneath it. Imagine taking a pendulum clock to sea. On a ship, a pendulum clock is worse than useless. Picture the deck of an old sailing vessel out on the open ocean. The ship rolls to one side as a swell lifts it, then pitches forward as it slides down into the trough, then heaves back the other way, and it does this endlessly, every few seconds, all day and all night, for weeks on end. Now hang your delicate pendulum in the middle of all that. The bob, which is supposed to swing freely and gently under the calm, honest pull of gravity, is instead being thrown around, shoved, tilted, lifted, and dropped by the motion of the ship itself. Its swing is no longer its own. The deck tips one way, and the pendulum can barely rise. The deck drops away beneath it, and the bob goes light and wild. The steady beat is shattered. The clock that kept 15 seconds a day on solid ground becomes a hopeless, staggering thing at sea, telling you nothing you can trust. And it gets worse, because there's a second problem waiting even if the sea were somehow calm. A pendulum's rhythm depends not just on gravity, but on the exact length of the pendulum, the distance from the pivot at the top down to the weight at the bottom. A longer pendulum swings more slowly, a shorter one swings faster. And what happens to the length of a metal rod when it gets warmer? It expands. It grows longer. And when it gets colder, it shrinks and grows shorter. So carry your pendulum clock from the cold of a northern port down into the sweltering heat of the tropics, as any long ocean voyage would, and the rod itself quietly stretches in the heat. The pendulum grows a little longer, and the whole rhythm of the clock slows down without anyone touching a thing. Temperature alone, over a long enough journey, is enough to ruin it. The very same rod that kept perfect time in a cool English hall would keep quite different time in the warm air of the Caribbean, and there was no easy way to know by how much. So here is the pendulum, this triumph, this 60-fold leap forward, this steady and beautiful oscillator that transformed timekeeping on land, and yet it carries within it two fatal flaws. It needs gravity to hold perfectly still and steady, which the deck of a ship absolutely will not do. And it needs its own length to stay perfectly fixed, which the changing warmth of the world will not allow. On dry, cool, solid ground, the pendulum was a marvel. The moment you carried it out onto the moving, warming, living world, it fell apart in your hands. And that, quietly, is the shape of this entire story, laid out in miniature right here at the beginning. Every clock we will meet tonight is wonderful, and every clock has a flaw, and each flaw sends us searching for the next clock. The pendulum's flaw is that it leans on things that will not stay still, on the steadiness of gravity, on the constancy of length. It borrows its rhythm from the physical world around it, and the physical world, it turns out, cannot be trusted to hold that rhythm steady. The ground moves, the air warms, the rod stretches, and a clock built on shifting foundations tells shifting time. Which raises the question that will pull us forward through the rest of the night, though we won't answer it fully for a long while yet. If you cannot trust the swing of a weight because gravity and warmth and motion all conspire against it, then what can you trust? What could you possibly build a clock out of that would not care whether it was on land or at sea, in the cold or in the heat, standing still or heaving on the waves? What repeating thing in all the universe keeps a rhythm so pure, so stubborn, so utterly its own, that nothing you do to it, nowhere you carry it, can knock it off its beat? We are a very long way still from that answer. It lives inside an atom, and we won't arrive there for some time yet. But you can already feel the shape of the longing, can't you? The dream of a clock that owes nothing to the world it sits in. A clock with a beat so perfect it could be carried across an ocean, up a mountain, into the sky, and never falter. And it was, in fact, an ocean that made people desperate enough to start truly hunting for that better clock. Because while a wobbly clock on land was merely an inconvenience, a wobbly clock at sea was a matter of life and death. Out on the open water, out of sight of any coastline, with nothing but grey sea in every direction to the flat edge of the horizon, sailors faced a problem so hard and so deadly that empires poured fortunes into solving it. It was a problem about knowing where you are, and, strangely, wonderfully, it turned out to be a problem about time, about knowing precisely what time it was, not where you stood, but somewhere far away, back home. The two things, where you are and what time it is, are far more deeply tangled together than they first appear, and untangling them would drive the next great leap in our long search for a perfect, unshakable tick. But before we sail out into all of that, let me leave the pendulum swinging there a moment longer in its tall wooden case in some quiet 17th century room. Tock, 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 that slow, even, wooden heartbeat that ruled the world's time for 3 centuries. It's a good sound to rest in. It's the sound of the first time human beings ever really pinned down a steady rhythm and counted it well. And if you listen to it in your mind, that patient wooden swing, you might notice how much it feels like breathing. In and out, over and back. The same gentle, unhurried repeat over and over, asking nothing of you, keeping its own quiet time in the dark. Let that be the rhythm we carry forward. Because everything else we're going to discover tonight, the chronometers built to cross oceans. The crystals that sing thousands of times a second, and at last the atoms that tremble billions of times a second and never ever tire, all of it grows out of that one simple, beautiful idea we found at the very start. A clock is a thing that repeats, and a way to count the repeats. And the whole long adventure of human timekeeping is just our search for a repeat we can finally, completely trust. A ring so pure it never fades. A beat that belongs to nothing and no one, and cannot be knocked off its rhythm by the rolling of a ship or the warmth of a summer's day. The pendulum was our first great beat. It swept away 15 minutes of daily error and left us with 15 seconds. It filled the halls of Europe with that lovely wooden ticking. And it failed, gently but completely, the moment we tried to carry it out to sea. So we would have to invent something new, something that did not care about gravity at all, something a sailor could bolt to the timbers of a pitching ship and trust across 10,000 miles of open water. And a man would spend most of his life building exactly that. Alone, mostly, misunderstood, often, chasing a prize that a nation had offered in something close to desperation, because ships full of men were sailing off the edges of their maps and dying for the want of a clock that could keep time on the waves. His name was Harrison, and his story is one of the quietest and most stubborn kinds of genius there is. The kind that gives 40 years of a single life to making one thing right. But that is where we're going next, out onto the cold grey water, into the century of tall ships and lost fleets, and a fortune offered to anyone who could solve the deadliest puzzle in navigation. So let your breathing settle into that old pendulum rhythm. In and out, over and back. There's no hurry at all. The tide isn't going anywhere, and neither are we. We have all night, and the whole slow story is still ahead of us, unfolding one gentle tick at a time. For now, just rest in what we've found. That underneath every clock that has ever existed, from the grandest cathedral timepiece to the phone glowing softly beside you, there is only ever that same simple pair of things. Something that repeats. And someone, or something, patiently counting. The pendulum gave us a good repeat, the best the world had ever known. And now, out on the restless sea, we're about to go looking for a better one, because the ocean, rolling and heaving and stretching every rod it touched in the tropical heat, had made the pendulum's beautiful swing worthless, and left the world hungry for a rhythm that answered to nothing but itself. So drift with me a little further into the dark. We're leaving dry land behind now, and the steady wooden ticking is fading behind us, and ahead there's only the sound of water against a hull, and the wind in the rigging, and a lone clockmaker, bent over his workbench by candlelight, trying to build a heartbeat that the sea itself could not stop. The sea, then, let's go to the sea. Picture it, sometime in the early 18th century, a clear night somewhere in the Atlantic, stars sharp overhead, the deck of a wooden sailing ship rising and falling on a long, slow swell. The navigator is standing at the rail, doing what navigators had been doing for centuries. He looks up. He reads the sky. He can tell, from the angle of a particular star above the horizon, exactly how far north or south he is. Latitude was a solved problem, had been for ages, and on a clear night you could nail it to within a few miles by measuring the altitude of the sun at noon or certain stars in the dark. That part worked. That part had always worked. But east and west, longitude, that was the thing that killed ships. Because longitude, where you are along the great circle of the globe, east or west of where you started, longitude is not something you can see. It's not written in the stars directly. You can't measure it by looking up. To know your longitude, you need to know two things at once. What time it is, right here, at your exact position on the ocean, and what time it is at some fixed reference point back home. The difference between those two times, converted into degrees, tells you how far east or west you've drifted. 4 minutes of time difference, 4 minutes between local noon here on the water and noon back in London or Lisbon, that's 1 degree of longitude. 1 degree. At the latitudes where most Atlantic trade routes ran, 1 degree of longitude could be somewhere between 50 and 100 kilometers of sea, depending on where you were. Get it wrong by an hour, just 1 hour, and you were perhaps 15 degrees off course. Out there in the open Atlantic, 15 degrees might be the difference between a safe harbour and a reef that would open a ship's hull like a letter. Ships were being lost. Whole convoys were wrecked. Men died in their hundreds. Cargoes, spices, silver, cloth, the extracted wealth of colonial trade went to the bottom. And every maritime nation with ships in the water knew it, and none of them could fix it. So in 1714 the British Parliament passed the Longitude Act and offered a prize. Up to £20,000, a sum that in the early 18th century would make a working man rich for several lifetimes, to anyone who could produce a practical method for determining longitude at sea to within half a degree. 30 miles. That was the standard. Get a ship's navigator to within 30 miles of true position reliably in open ocean, and the prize was yours. Dozens of proposals arrived. Some were ingenious, some were absurd. There was a scheme involving wounded dogs and a mystical powder. There was a network of signal ships anchored across the ocean at fixed positions. There were lunar calculations so complicated that a skilled navigator, even if he could do the maths correctly, would need hours of work for a single position fix. The astronomers had their own approach, carefully observed tables of the moon's position against background stars, the so-called lunar distance method, which did eventually work after a fashion, but was slow and difficult and required a kind of mathematical patience that few practical sailors could sustain in the middle of a voyage with the weather closing in. And then there was John Harrison, a carpenter's son from Lincolnshire, largely self-taught, with a gift for mechanical things that was simply one of those rare, inexplicable accidents of human nature. Harrison had been making wooden clocks since he was a young man. Not merely serviceable clocks, extraordinary ones, clocks with wooden gear teeth that needed no lubrication and resisted temperature changes, clocks with elegant solutions to friction that had troubled clockmakers for generations. He understood, at a fundamental level, the problem of a clock's oscillator. The thing that beats, the thing whose regularity determines everything. He understood that a pendulum was magnificent on dry land and useless on a ship. And he understood exactly why. A pendulum's period, the time it takes to swing from one side to the other and back, depends on its length and on the local strength of gravity. Change the length by a temperature shift that expands or contracts the metal, and the period changes. Tilt the pendulum, disturb its plane of swing, and it's no longer behaving the way the equations demand. A rolling deck combined both disasters simultaneously. It pitched and heaved and introduced false forces, and the tropical heat that sailors sought in trade route waters expanded every metal rod and changed every carefully calibrated length. A pendulum clock on a ship gained or lost time at a rate that made it useless for navigation. The oscillator was too sensitive to its environment. The clock was listening to the wrong things. Harrison's insight, the thing that would eventually win him the prize and change navigation, was that the oscillator needed to be isolated from the world. Not a pendulum governed by gravity, but a balance wheel and a spring, a mass on a rotating axis governed only by the restoring force of the spring itself, not dependent on which way was down, not sensitive to how the deck was leaning. He worked on this for decades, producing a series of marine chronometers he called H1, H2, H3, each a brilliant piece of engineering, and each still not quite right in some way he kept finding and correcting. H1 he completed in the early 1730s, and it was already extraordinary. H3 occupied him for almost 20 years. And then, late in his life, Harrison built H4. H4 was completed in 1759, and it was unlike anything he had made before. Where the first three chronometers had been large, complex machines, beautifully worked but still essentially elaborate, H4 was small, a pocket watch, roughly 5 inches across, elegant and spare. Its oscillator was a high-frequency balance wheel running at 5 beats per second, paired with a temperature-compensated spring whose restoring force changed in just the right way with temperature to cancel out the thermal expansion of the wheel itself. Every source of error that had crept into earlier designs was met, thought through, and answered. It was not a perfect object. Harrison, who was his own sharpest critic, knew its remaining flaws better than anyone. But it was close. It was very close. In 1761, H4 set out on a sea trial, a voyage to Jamaica aboard the Deptford, with Harrison's son William as its keeper. The voyage lasted 81 days. When they arrived at Port Royal and compared H4 to local astronomical time, it had lost 5 seconds. 5 seconds. Over 81 days at sea, through tropical heat and Atlantic storms, and the constant motion of a wooden hull on open water, the balance wheel inside that small, glittering case had never varied by enough to matter. 5 seconds of error over nearly 3 months, well within the standard the Longitude Act required for the prize. It was a remarkable thing. What Harrison had done, really, was find an oscillator that answered to itself rather than to its surroundings, a rhythm that the ocean could not disrupt, because it did not depend on gravity or stillness or temperature in the ways that had always betrayed clocks before. The feedback of the environment had been broken. The spring remembered its natural frequency and held it, and the clock ticked steadily in the dark below decks while the ship heaved and rolled and made its long passage south. The practical upshot was navigation, longitude solved, at least well enough, at last. Ships could carry a chronometer set to Greenwich time, compare it to local noon, and know where they were within a few miles. Fleets could navigate with confidence. The death toll from navigational uncertainty began, slowly, to fall. And buried inside that practical gift was a conceptual one that wouldn't be fully unwrapped for another 2 centuries, the idea that the best oscillator is not the one most beautifully constructed, but the one most immune to disturbance. Harrison had found that principle in a balance spring. Others, much later, would find it somewhere far stranger. But for now, rest with the sound of that little watch. 60 ticks per minute, steady as breathing, below the waterline of a ship rocking on a dark tropical sea. It's a good sound, a patient sound. And we can stay with it for a moment before we follow the thread a little further forward. A few generations after Harrison, in a Paris laboratory in the autumn of 1880, 2 brothers were pressing thin slices of crystal between metal plates and watching something odd happen. Their names were Jacques Curie and Pierre Curie, and they were studying the relationship between mechanical stress and electricity in crystals. They had a hypothesis, drawn from some theoretical considerations about crystal symmetry, that certain crystals, quartz was one of them, and so was tourmaline, and Rochelle salt, would generate a small electric charge when you squeezed or bent them. A mechanical deformation, they thought, should displace the electric charges bound inside the crystal's structure in a way that produced a measurable voltage at the surface. They were right. They pressed their crystals, and the voltmeter moved. Squeeze a piece of quartz and it generates electricity. Not much electricity, tiny amounts, detectable only with sensitive instruments, but real. Reliably reproducible, predictably proportional to the degree of deformation. They called it the piezoelectric effect, from the Greek word for pressure, and they published their finding and moved on to other things. What they didn't immediately pursue, though they were aware of the theoretical possibility, was the reverse. If squeezing a crystal generates a voltage, then applying a voltage to a crystal should squeeze it, should make it deform, physically, slightly, in proportion to the applied electric field. The reverse piezoelectric effect was demonstrated the following year, and it completed a picture that would, eventually, become the basis for billions of devices. Because what you now had was a crystal that could be made to vibrate mechanically by an oscillating electric signal. And that vibration would in turn generate an oscillating electric signal of its own. And if you fed that back on itself in the right way, the crystal would lock on to one particular frequency and ring there steadily, like a bell that had been struck and never quite stopped. A crystal's resonant frequency, the frequency at which it most naturally and enthusiastically vibrates, depends on its physical dimensions, its shape, the orientation of the cut relative to its internal crystal structure. Engineers learned to cut quartz in particular ways to push the resonant frequency where they wanted it. And a well-cut quartz crystal has a very high Q factor, that measure of how sharply and stubbornly it prefers its own frequency, how reluctant it is to be pushed off it by noise and disturbance. Much higher than a balance spring, much higher than a pendulum. It took several decades for all of this to come together into a practical timekeeper. Radio engineering in the early 20th century required precise frequency references, and quartz oscillators were developed for that purpose first. Then someone asked the obvious question. If a quartz crystal oscillates at a known stable frequency, and we count those oscillations, do we have a clock? In 1927, at the Bell Telephone Laboratories in New York, an engineer named Warren Marrison and his colleague J.W. Horton built one and answered yes. The first quartz clock. It had no pendulum, no balance wheel, no escapement, no clicking, mechanical gate that let the gear train advance one tooth at a time. There was nothing visibly moving at all. Nothing you could watch with your eye and understand intuitively as a clock's heartbeat. Inside its cabinet, a thin slice of quartz was vibrating at a frequency far above human hearing, converting that vibration into an electrical signal, which was divided down through electronic circuits into a frequency you could actually use to drive the hands of a clock face. The oscillator was invisible. The rhythm was in the crystal. Marrison and Horton's clock was immediately more accurate than any mechanical clock that had ever existed. Over short periods, hours, days, it held its rate far better than the best pendulum designs, because quartz doesn't experience the friction of an escapement, doesn't depend on gravity, isn't disturbed by air currents or the slight lean of a floor. It just vibrates. But quartz has its own vulnerabilities. A quartz crystal's resonant frequency shifts slightly with temperature. The speed at which its atoms move depends on how warm or cold they are, and that changes the elastic properties that determine the resonant pitch. It shifts with age as microscopic changes in the crystal's internal structure accumulate over years. It shifts with mechanical stress if the crystal is jarred or pressed. These are small effects, much smaller than what afflicts a pendulum or a balance spring, but they are not zero. Over a week or a month or a year, even a well-made quartz oscillator will drift slightly from its nominal frequency, and that drift, accumulated, becomes an error. A quartz wristwatch running at 32,768 Hz, that particular frequency chosen because it is 2 raised to the power of 15 and so divides beautifully down to 1 second per second through a simple chain of electronic halving, might gain or lose 15 or 20 seconds a month if it isn't corrected. A laboratory-grade quartz standard housed in a temperature-controlled oven could do much better. But it still drifts. And so the question reasserted itself, the same question that had shadowed every clock since Huygens. If you want to know how much the quartz is drifting, if you want to catch its errors and correct them, you need something even more stable to measure it against. You need a reference. You need a master. And the master, for almost a century, had been astronomical time. The rotation of the Earth, the position of the stars, the carefully observed motions of the solar system reduced to numerical tables by generations of astronomers. The sky told you the true time, and you corrected your clocks against it. That worked, as long as you believed the sky was reliable, and for most of human history it seemed absurd to doubt it. The Earth turns, the sun rises and sets, the day is the day. What could be more stable, more dependable, more fundamentally given than the turning of the planet you stand on? In the 1940s, a man named Isidor Isaac Rabi began to suspect that this confidence was misplaced. Rabi was an American physicist born in 1898 in a small town in what is now Poland, raised in Brooklyn. Educated at Cornell and Columbia and then in Europe during the golden age of quantum mechanics, and by the 1930s one of the most inventive experimental physicists working in the United States. His great technical achievement was a method he developed in the late 1930s called molecular beam magnetic resonance. It's worth understanding what this means, because it opens the door to everything that comes after. Atoms and molecules, which are groups of atoms bonded together, have internal structures that behave like tiny magnets. The nucleus of an atom has a magnetic moment, a kind of orientation in space. So do the electrons surrounding it. These magnetic orientations can be flipped between discrete states by applying electromagnetic radiation at exactly the right frequency, a frequency determined by the atom's own internal quantum mechanical architecture, by the energies of those different magnetic states, by the laws of physics that govern how matter behaves at the smallest scales. If you get the frequency exactly right, atoms absorb the radiation and flip. If you're slightly off, they don't. What Rabi and his group at Columbia learned to do was pass a beam of atoms or molecules through a precisely controlled sequence of magnetic fields and a small region where they could be irradiated with electromagnetic waves of a chosen frequency. By watching how the beam was deflected, different states deflect differently in a magnetic field, they could detect, with extraordinary sensitivity, when the radiation frequency matched the atom's resonance. When it matched, states changed. The beam changed. You could see it. This was a method for measuring atomic frequencies with a precision that earlier instruments couldn't approach, and Rabi's group used it to map the magnetic properties of dozens of nuclei with an accuracy that transformed atomic physics. In 1944, he was awarded the Nobel Prize in Physics. And in 1945, after the war had ended and physicists were finding their way back to purely scientific questions, Rabi said something in public that seemed almost casual, but contained the seed of the next great revolution in timekeeping. He suggested at a conference, in a remark that circulated through the physics community, that atomic resonances could serve as frequency standards, as the basis for clocks, that rather than trusting hand-made oscillators corrected against astronomical observations, you might instead let an atom define the second. The reasoning behind this suggestion is worth sitting with, because it's beautiful in its simplicity. Every cesium atom in the universe is identical. Not approximately identical, not nearly the same, identical in the strict quantum mechanical sense, in a way that no two man-made objects can ever be. If you pick up a cesium-133 atom from a laboratory in Boulder, Colorado, and another from a laboratory in Tokyo, and another that has been drifting in interstellar space for the last 5 billion years, they are the same object, same mass, same electron configuration, same nuclear structure, same energy levels, and the frequency at which they resonate, the frequency of the radiation that flips the magnetic orientation of the outer electron relative to the nucleus, the so-called hyperfine transition, is the same for all of them, everywhere, always, determined not by how they were made or how old they are or how warm their surroundings are, but by the fundamental constants of nature, constants that do not change. A pendulum can be made badly. A balance spring wears with use. A quartz crystal ages, drifts with temperature, varies between individual samples cut from different parts of the same rock. Every human-made oscillator is, to some degree, a particular thing. This pendulum, this crystal, this spring, and particularity means variability. No two are exactly alike. No one of them stays exactly the same over time. They are, all of them, approximations to the frequency they were meant to have. An atom makes none of these compromises. It is not manufactured. It cannot wear out. It doesn't have a temperature coefficient in the way a quartz crystal does, or at least not one that can't be controlled. It is simply what it is, a physical system governed by quantum mechanics, with energy levels spaced apart by amounts that are fixed by the laws of the universe. Its resonance frequency is not something we chose or constructed. It is something we discovered, something already there, waiting to be read. This was Rabi's insight. Not the technical details, those would take another decade to work out, but the conceptual turn. Stop trying to build the perfect oscillator by hand. Find one that nature has already built perfectly. Find a frequency that is not manufactured, but measured. Find a clock that the universe itself has been running since atoms first existed. The particular transition in cesium-133 that would become the heartbeat of the modern second is the hyperfine transition of the ground state. Let's take that slowly, because it's the kind of phrase that can slip past without landing, and it deserves to land. The cesium-133 atom has one electron in its outermost shell, orbiting a nucleus that contains 55 protons and 78 neutrons. That outer electron has a property called spin, a quantum mechanical quantity with no perfect classical analogue, but which behaves, for our purposes here, something like a tiny bar magnet oriented in space. The nucleus also has a magnetic orientation, a nuclear spin. And these two magnetic orientations, the electrons and the nucleuses, can be aligned in two ways, parallel to each other or antiparallel. Parallel to each other and antiparallel to each other are two distinct energy states. Not one state, two states, with a tiny difference in energy between them. Now, quantum mechanics tells us that an atom can transition between these states by absorbing or emitting a photon, a particle of light, whose energy exactly matches the gap between the states. And since the energy of a photon is directly related to its frequency, this transition happens at one specific frequency, determined by the size of that energy gap. For cesium-133, that frequency is in the microwave range. It was not known precisely before 1955, but it was understood to be somewhere near 9.5 gigahertz, 9.5 billion oscillations per second, and it was understood to be the same for every cesium-133 atom that had ever existed. The challenge was not philosophical. Everyone with a grounding in atomic physics could see, once Rabi had framed it clearly, that this was the right place to look for a better clock. The challenge was experimental. How do you actually make a clock out of an atomic resonance? How do you get the atoms and the microwave radiation and the detection all working together in a way that gives you a stable, usable output? How do you turn a quantum mechanical property of a gas of invisible atoms into a number that ticks off the seconds? That question, once Rabi had asked it, would consume the best years of several brilliant careers. And the first people to answer it completely. To build a machine that actually worked as a cesium atomic clock and could be trusted as a primary standard were a pair of physicists working in a laboratory just outside London. They would spend years on a problem that, in principle, everyone knew was solvable, and their answer, when it finally came, would change the definition of the second itself. But they're a few years ahead of us yet. For now, let the idea of the cesium atom settle quietly in your mind. Every atom of it in the universe, identical, every atom of it, vibrating to the same internal music, a frequency determined not by any human hand, but by the structure of matter itself. We don't have to understand every detail of why that energy gap is the size it is, or how quantum mechanics produces it. You don't have to hold any of that precisely. The idea is enough that inside each of those tiny, utterly anonymous atoms, there is a clock that has been running since the atom first formed, and it has never varied, and it never will. That's a strange thought to carry into sleep, maybe, the idea that time is being kept inside matter itself, in the flickering back and forth of an electron spin, in the absorption and emission of microwaves too faint to feel and too fast to conceive of, that every atom of a certain element is a timekeeper, that the universe has been counting this frequency since long before there were any human beings around to notice or care or try to listen. But before we listen, before we build the machine that finally hears what the cesium atom has been saying, we should pause here and let a few things quietly settle into place. We've come a long way from Huygens and his pendulum. We've crossed the oceans with Harrison. We've watched the quartz crystal start to vibrate in a Bell Telephone laboratory in 1927 and found that even this extraordinary thing, with no moving parts you could see, still drifted, still aged, still needed correcting. And now we've arrived at the atomic idea, the suggestion that an answer exists inside matter itself, that the right oscillator has been there all along, waiting. The path from Rabi's suggestion in 1945 to a working cesium clock is not a straight line. It required new techniques, new instruments, years of careful experiment. It required not one person, but several, at different institutions, in different countries, some of them aware of each other's work, and some of them not. And when the machine finally worked, it raised a question that was as philosophical as it was technical. What exactly do you compare it against, in order to know that it's right? If you're trying to build a clock better than anything that exists, how do you calibrate it? The answer: comparing the cesium frequency against the only standard then available, which was astronomical time, the slow turning of the Earth. Contained within it the seeds of the inversion. Because once you had measured the cesium frequency against the Earth's rotation precisely enough, you could ask the question the other way around: why are we using the Earth to define the second at all, instead of the atom? That question, once asked, never went away. So let your eyes be closed now, if they want to be. Let the details soften at the edges, the way it does when a story becomes a current you're floating in, rather than a thing you're actively following. John Harrison's watch is still ticking somewhere, behind us now, in the dark below the waterline of a ship on a long-ago sea. The quartz crystal is ringing in its laboratory in New York, high and inaudible, a frequency so far above hearing that it exists only as a number, a measurement, a steady electronic pulse. And somewhere in the air around you, in the cesium atoms that are drifting through every room in the world, the hyperfine transition is happening and happening and happening at the same frequency it always has, patient and exact and utterly indifferent to whether anyone is counting. That counting, the serious, careful, difficult business of actually counting, is where we're going next. To a laboratory in Teddington, a suburb southwest of London, in the early years of the 1950s. Two men, a collection of precision instruments, and the first real attempt to make an atomic clock that worked. And underneath all of it, still ticking with a patience that has outlasted every civilization that ever looked up at the stars and tried to read the time in them, the atom. Quiet, steady, identical to every other atom of its kind in every corner of the universe. The best oscillator that has ever existed, because nature built it, and nature does not have bad days. Just drift with that for a little while. There's no hurry. The story has been waiting for thousands of years to reach this point, and it can wait a few more minutes while you rest. So, Teddington then, it is the early 1950s, and Teddington is a quiet place, a suburb that sits southwest of central London, close enough to the city to hear its faint rhythms on a still night, far enough away that you could spend a morning in one of its long green spaces and forget entirely that the capital existed. The National Physical Laboratory, the NPL, as everyone who works there calls it, occupies a handsome Victorian building on the edge of Bushy Park, and it has been the place where Britain measures things carefully and officially since 1900. Lengths, temperatures, electrical standards, the invisible quantities that underpin everything else. And now, in these early years of a decade that still felt tentative after everything the previous decade had cost, two men were trying to measure time. Their names were Louis Esson and Jack Parry. Esson was a metrologist, a specialist in measurement, with a particular feeling for frequency and for the precise, patient work of making instruments do better than they had done before. He had spent years studying quartz oscillators, which by the 1950s were the finest clocks most people had ever seen or heard of. He knew their limitations. He knew the way they drifted, the way temperature reached inside them and shifted their frequency by tiny amounts, the way they aged almost imperceptibly, molecule by molecule, stress redistributing itself through the crystal in ways that nothing could fully predict. He knew that quartz, for all its elegance, was still a human thing, a made thing. And made things have flaws. Rabi's idea, floated in 1945, already known in the small world of precision metrology, was that atoms were different. Not made, but found. Not manufactured, but discovered. And if you could interrogate an atom's own internal resonance, that resonance would be the same everywhere and always, because atoms do not age, do not wear, and do not have bad manufacturing days. Essen wanted to find out if this was actually true, not as a philosophical proposition, as a measurable fact. The apparatus that he and Parry built was not small. It filled a significant portion of a room, a long assembly of vacuum chambers and magnetic hardware and precision electronics that looked, if you stood at one end of it and squinted, rather like a very serious piece of scientific plumbing. Which, in a sense, it was. They were routing atoms the way a plumber routes water, but the atoms were cesium atoms, and the path they followed was one of the most precisely controlled in the history of measurement. Cesium is, in ordinary life, an unremarkable element, soft, almost liquid at room temperature, silvery gold in its pure form, atomic number 55. It reacts violently with water and is not something you would want to handle carelessly. But its electronic structure, the specific arrangement of its electrons, and the orientation of its outermost electron relative to its nucleus, makes it useful in a way that has nothing to do with its chemistry. It has a transition, a very specific, very sharp, very reproducible resonance between two energy states of that outer electron, driven by the interaction between the electron's spin and the magnetic field of the nucleus. The technical name for this is a hyperfine transition, which means it arises from an extremely fine splitting of the atom's energy levels, caused by magnetic interactions inside the atom itself. Hyperfine, in this sense, means small but not vague. It means precise. It means that when an outer electron flips between its two orientations, the energy it either absorbs or releases corresponds to electromagnetic radiation at a specific frequency, a frequency so stable and so reproducible that it is the same in every cesium atom that has ever existed. That frequency is in the microwave range, roughly 9.25 gigahertz, a little more than that, in fact, but we will get to the exact number in a moment. What Essen and Parry were doing in that room in Teddington was trying to find it. The basic idea is this, and try to stay with it even if the details blur a little at the edges, because the picture will settle. You heat cesium in a small oven until it produces a beam of atoms, a thin, directed stream of them, drifting like smoke in a tunnel, if the smoke were moving in a perfectly straight line and had the mass of atoms rather than particles of soot. That beam enters a long tube under vacuum. It passes through a magnetic field that acts as a gate, a selector, sorting the atoms into two groups according to which of the two hyperfine states they happen to be in. Imagine sorting a crowd of people into left-handed and right-handed and directing only one group forward while the other is deflected away. The selector keeps one state, discards the other. Then the remaining atoms, all in the same state, like a crowd where everyone is holding up the same hand, enter the heart of the instrument. The heart is a cavity, a microwave cavity, a carefully machined metal enclosure through which microwaves are directed at the passing atoms. And if the frequency of those microwaves is exactly right, exactly the natural resonance frequency of the cesium hyperfine transition, something happens to the atoms as they pass through. They flip. The outer electron, which had been oriented one way, is nudged by the microwave energy into the other orientation. The atom changes state. It goes from one to the other, the way a coin flipped in the air comes down on the other side, except that this flip is caused by resonance, by the microwave frequency exactly matching the atom's own internal preference. After the cavity, the atoms pass through a second selector and reach a detector. and the detector simply counts how many atoms have flipped. If the microwave frequency is exactly right, the flip count is at its maximum. If the frequency drifts even slightly, the flip count falls. The difference is measurable. And this is how you find the frequency. You scan the microwave source up and down, watching the detector. And you look for the peak, the maximum, the exact resonance. That number, that frequency at which the most atoms flip, is the frequency of the cesium hyperfine transition. This is not instant. It is slow, deliberate, careful work. The kind of work that takes months, that requires constant attention to sources of error, that demands the kind of temperament that can look at a near-perfect measurement and ask what is still wrong with it. But by 1955, Essen and Parry had it. They announced their result, the first accurate cesium atomic clock operational at the National Physical Laboratory in Teddington. Now, here is where it gets quietly strange. Having an atomic clock is one thing. Knowing what number to assign to its frequency is another. Essen and Parry had built a device that vibrated at the cesium hyperfine transition. But to say that this frequency was 9 billion and something oscillations per second, they needed to know what a second was. And in 1955, a second was still defined by the rotation of the Earth. It was still at that point a fraction of a day. So they had to calibrate their atomic clock against the astronomical definition of the second. And to do that, they needed a very precise measurement of the Earth's rotation, which meant looking at the sky. They collaborated with William Markowitz, an astronomer at the U.S. Naval Observatory in Washington. The U.S. Naval Observatory had been the official keeper of American time for nearly a century. It sat on the high ground of northwest Washington, its domes overlooking the Potomac, and it had been measuring the passage of stars across the meridian, the traditional method of keeping astronomical time with extraordinary care. Markowitz was working with a type of astronomical time called the ephemeris second, which was based on the Earth's orbit around the Sun rather than its daily rotation, and was considered the most stable astronomical time standard available. The collaboration between Essen at Teddington and Markowitz in Washington lasted roughly 3 years, from 1955 to 1958, and at the end of it, they had a number. The number is this: 9,192,631,770. 9,192,631,770. That is how many complete oscillations of the cesium-133 hyperfine transition occur in 1 second, as the second was defined by the astronomical standard of the time. Essen and Markowitz measured it, and it was written down, and it did not go away. Sit with that number for a moment if you like. There is no need to memorize it. But it is one of the fixed points of the modern world, one of the numbers that everything depends on, invisibly, and there is something gently worth knowing about its history. It was not chosen, it was not rounded, it was not a convenient fiction agreed upon for simplicity. It was measured. It emerged from the patient comparison of a cesium beam clock in a London suburb and the transit of stars across the meridian in Washington, and it was what it was, a real count, a real frequency, the specific number that nature produced. 9,192,631,770. Now breathe. You are allowed to let it go. What happened next was slow to develop, but enormous in consequence. Throughout the late 1950s and early 1960s, more and more atomic clocks were built. The technology spread to other national laboratories. Comparison measurements were made, and each time the cesium frequency came back the same. Not almost the same. The same. Because every cesium-33 atom in the universe is, as Rabi had argued a decade earlier, identical to every other. There is no variation to average out. There is no drift to compensate for. The number is the number. And gradually, inside the world of metrology, a quiet consensus was forming. The Earth was no longer the right thing to ask about time. The atom was. The meeting that made this official happened in Paris in 1967. The organization responsible was the Conférence Générale des Poids et Mesures, the General Conference on Weights and Measures, the body that governs the international system of units. Its 13th session, convened that year, included representatives from dozens of nations, and its business included a proposal that was, in retrospect, one of the most philosophically significant decisions in the history of measurement. The proposal was to redefine the second. Before 1967, the second was a fraction of a day. Specifically, it was 1/86,400th of a mean solar day, the average day, as the Earth turned. This had been the definition in one form or another, since time began to be formally recorded. A day is what happens between one sunrise and the next, or between the sun reaching its highest point and returning to it. Divide that into equal pieces, and the pieces are seconds. The planet was the clock. The sky was the reference. After 1967, the second was 9,192,631,770 periods of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. The 13th General Conference on Weights and Measures voted to adopt this definition. And with that vote, time, formal, official, SI time, detached from the Earth. This is the inversion, and it is worth staying with it for a moment, because it is not a small thing. For every civilization that had ever existed, up to that point, the planet had been the clock. The sun rose and set, and the time between those events was divided into units, and those units were called seconds and minutes and hours, and this was what time meant. The Earth was assumed to be reliable. It was assumed to be consistent. It was, after all, the largest and oldest thing most people could conceive of, and it had been turning, as far as anyone could tell, for as long as there had been anyone to notice. But in 1967, the definition was inverted. The second was no longer a slice of the planet's rotation. It was a fixed count of oscillations inside an atom. And the planet, the spinning Earth, the rising and setting sun, the thing that had defined time for every human being who had ever lived before that year, became the thing that had to be measured against the atom. And corrected. Because the Earth, it turned out, was not a very good clock. Not a bad clock, in the loose, everyday sense. If all you need is a rough indication of where you are in the day, the Earth is fine. It has been working well enough for a few billion years. But for the purposes of precision, for navigation, for communications, for the synchronization of global infrastructure, the Earth is erratic in ways that matter. The first problem is systematic. The Earth's rotation is slowing down, very slowly. Over the span of a human lifetime, you would not notice. But averaged over long periods, the Earth's day lengthens by roughly 1.5 to 2 milliseconds every century. A millisecond and a half sounds negligible, and in daily life it is, but in a world where atomic clocks can measure time to fractions of a nanosecond, a billionth of a second, a millisecond is a large and easily detected discrepancy, and the cause of this slowing is not mysterious. It is the moon. The moon's gravity pulls on the Earth, and particularly on the oceans. The tides, those vast movements of water that fill and empty harbours twice a day, are the visible result of that pull. But the oceans are not fluid in the way that air is fluid. They have friction with the ocean floor and the coasts. And that friction acts as a kind of brake on the Earth's rotation, transferring a tiny amount of rotational energy to the moon's orbit, pushing the moon slowly outward, lengthening our days by that small but real amount. This has been going on since the moon formed, several billion years ago, and it will continue until tidal forces have done whatever they are going to do with the Earth-Moon system, which is a very long way off. For now, it simply means that the day, measured in seconds, is not the same length it was a century ago, and will not be the same length a century hence. This alone would make the Earth a poor clock by atomic standards. But the second problem is worse, in a practical sense, because it is unpredictable. The Earth's rotation does not slow smoothly. It wobbles, it speeds up occasionally, it slows irregularly. The reasons are complex, and not all of them are fully understood. The movement of mass within the molten core, the redistribution of weight by glaciers melting and oceans warming, the seasonal shifting of atmospheric pressure, the movement of groundwater. All of these things and others affect the planet's rotation in ways that cannot be predicted more than a few months in advance. This is the deep problem. A systematic drift can be modelled and corrected for. An unpredictable wobble cannot. And if your definition of the second depends on the Earth's rotation, then the second itself becomes unpredictable. It might be slightly longer today than it was last Tuesday, and slightly shorter than it will be next spring, and there is no way to know in advance by how much. For ordinary life, this does not matter. But for the systems that modern civilization runs on, GPs, telecommunications networks, financial transactions, the synchronization of servers across continents, it matters enormously. And here is the detail that is perhaps the strangest of all, the one that feels most like the present sneaking into a deep historical pattern. In the early 2020s, the Earth began, on some individual days, to spin slightly faster than usual. Not by much, but enough for the atomic clocks to notice. Enough that, for the first time since the invention of the leap second, scientists began discussing the unprecedented possibility of a negative leap second, removing a second from the calendar rather than adding one to compensate. The Earth, in other words, overshot. It was going too fast for the first time in the short history of precision timekeeping. We will come back to leap seconds. For now, the point is simply this: the planet is not reliable. It never was, quite, and from 1967 onward, we have had a definition of time that does not rely on it, and the planet's rotation has been something we measure and adjust for rather than something we trust. The atom is the master, the Earth is the error. Let that be a thought that floats for a few seconds, if you like. There is a quiet strangeness in it that bears sitting with. You are lying somewhere comfortable, in a room that sits on the surface of a planet that has been wobbling unpredictably since before there were human beings to notice, and the clocks that govern your world do not ask it what time it is. They do not need to. The cesium atom knows. So let's go slowly back inside the clock, because the mechanism is worth understanding, and understanding it is easier than it sounds, and there is something almost calming about the precision of it once you see how it fits together. We left the cesium beam passing through the microwave cavity. Let us start a little earlier and walk the whole path at a gentle pace. The clock begins with heat. A small oven, no larger than your fist, in many designs, heats cesium metal until atoms begin to evaporate from its surface and drift outward. They exit through a narrow opening, a slit, and the geometry of the apparatus means that only atoms moving in roughly the right direction continue forward. The rest hit the walls and are absorbed. What emerges on the other side of the first slit is a beam, not dense, not dramatic, not anything you could see with your eye, but a thin, steady, directed drift of cesium atoms, moving forward through the vacuum of the apparatus at moderate thermal speeds. These atoms are in various states. Some have their outer electron oriented one way relative to the nucleus's magnetic moment, some the other. This matters, because only atoms in the right starting state will give you useful information about the resonance. You need to sort them. The first magnetic selector is a strong, carefully shaped magnetic field that deflects atoms according to their state. Think of it like this. If you rolled two different types of ball along a ramp that had a magnet embedded in it, and one type was slightly magnetic while the other was not, the magnetic ball would curve and the non-magnetic ball would continue straight. Something like this happens here. The two hyperfine states of cesium respond differently to the magnetic field. One is deflected one way, the other another, and the geometry of the apparatus is arranged so that only atoms in one particular state continue through to the next stage. The other state is discarded. Now you have a beam of atoms, all in the same hyperfine state. They move forward into the interaction region, into the cavity. The cavity is the crucial part. It is a precisely machined metal enclosure through which the beam passes, and through which microwaves are also introduced. The microwaves come from an oscillator, in practice, a quartz crystal oscillator whose frequency has been multiplied up into the microwave range to somewhere near that number, 192,631,770 Hz, nearly 9¼ gigahertz. The microwaves fill the cavity, and as the cesium atoms pass through, the microwave field interacts with them. If the microwave frequency is exactly on resonance, exactly matching the natural frequency of the cesium hyperfine transition, the interaction is coherent. The atoms absorb the microwave energy and flip their electron orientation, changing from the first hyperfine state to the second. They emerge from the other end of the cavity in the other state. If the frequency is slightly off, even a little, the interaction is less coherent, fewer atoms flip, and the output at the detector decreases. After the cavity, the atoms pass through a second magnetic selector. But this one is arranged to let through only atoms that have flipped, only atoms that are now in the second hyperfine state. Atoms that did not flip are deflected away. The atoms that made it through hit a detector, which produces a signal proportional to how many atoms arrived. So the signal from the detector is a measure of how many atoms flipped, and the number of flipped atoms is highest when the microwave frequency is exactly on the atomic resonance. This gives you a control signal, a feedback signal, and this is where the clock actually closes its loop. A piece of electronics watches the detector signal continuously. When the frequency is perfectly tuned, the signal is at its maximum. If the frequency drifts upward by any tiny amount, the signal drops. The electronics detect the drop and adjust the microwave oscillator, nudge it back down. If the frequency drifts too low, the signal drops the other way, and the electronics nudge it upward. This is called a servo loop, or sometimes a feedback loop. The quartz oscillator at the heart of the system is being constantly corrected, disciplined, the word in the field is, by the cesium atom's resonance. The atom sets the standard. The quartz does the counting. The feedback loop keeps the quartz honest. The output of the clock, the actual ticking, the signal you use to count time, comes from this disciplined quartz oscillator. Not directly from the atom. The atom is more like a reference, a constitutional standard, against which the quartz is continuously measured and adjusted. The quartz is fast and convenient. The atom is true. And the key insight, the one worth sitting with, is that the atom cannot be bribed. It cannot be persuaded. It does not have a manufacturing tolerance. Every cesium-133 atom in the universe responds to the same microwave frequency. If you build this clock in Teddington, or in Boulder, or in Tokyo, or on a research vessel in the middle of the Pacific Ocean, the cesium hyperfine transition is the same. The feedback loop converges on the same number. The atom is not a standard agreed upon by committee. It is a standard written into the structure of matter, and no human decision or political circumstance can change it. This is why Rabi's proposal from 1945 was so powerful. It was not just that atomic clocks were more accurate than quartz. It was that they were accurate for a reason that was immune to the ordinary sources of error. A quartz clock drifts because quartz is a physical object in a physical world, subject to stress and temperature and time. A cesium beam clock is anchored to a transition that exists independently of the apparatus that measures it, independently of who built the apparatus, and independently of where on Earth or off it the measurement is being made. Now, there is one more thing to add to the mechanism, and it matters a great deal. It is the contribution of Norman Ramsey. Ramsey was an American physicist who had worked with Rabi and then developed his own techniques for precision spectroscopy, for probing the fine structure of atoms with very high resolution. And the problem he identified with the simple cesium beam, as I have described it, is this. The atoms spend very little time inside the cavity. They pass through quickly. And the less time an atom spends interacting with the microwave field, the less sharply defined the resonance is. The peak in the detector signal, the maximum that tells you where the resonance lies, is broad rather than sharp. And a broad peak is harder to find the center of with precision. Ramsey's insight was to split the interaction into two. Instead of one long cavity, he used two short ones, separated by a gap. The atoms pass through the first cavity and receive a partial interaction, a kind of first nudge from the microwave field. Then they travel through a quiet field-free region, carrying the memory of that interaction internally in the quantum state of the electron. Then they pass through the second cavity, which gives them a second nudge. If the frequency is right, the two nudges add coherently and the electron flip is complete. If the frequency is wrong, they interfere partially or destructively, and the flip doesn't happen. The crucial point is that the atom accumulates its interaction over the entire distance between the two cavities, a much longer effective interaction time than a single cavity could provide, and this produces a much narrower resonance peak. The signal sharpens. The measurement becomes more precise. You can find the center of the peak more accurately, and so you can control the microwave frequency more tightly against the atomic resonance. This technique is called the method of separated oscillatory fields, or Ramsey interrogation. It became the standard for cesium beam clocks and for a wide range of other precision instruments. Norman Ramsey received the Nobel Prize in Physics in 1989 for this and related work. The prize was not just for the technique in isolation, but for a body of work that fundamentally shaped how physicists and metrologists interrogate the quantum world. Ramsey interrogation is, in some form, at the heart of nearly every precise atomic clock built in the decades after he published his method. And so the Cesium beam clock, as it stood by the 1960s, was this: an oven, a beam, a first magnetic selector, two short microwave interaction zones with a quiet gap between them, a second selector, a detector, a feedback loop, and a disciplined quartz oscillator. The whole thing is a machine for asking Cesium what frequency it prefers, and then locking an oscillator to that preference and counting the oscillations as they come. It is not complicated in outline. The complications are in the details, the magnetic shielding that keeps stray fields from perturbing the atoms, the vacuum system that keeps residual gas molecules from scattering the beam, the temperature controls that keep the cavity stable, the electronics that are sensitive enough to detect tiny changes in the detector signal and translate them into equally tiny corrections to the oscillator. All of these are engineering challenges, and all of them were solved, slowly and carefully, over the decades following Essen and Parry's first device. Each solution made the clock more stable, more accurate, more able to run unattended for longer periods. The clocks got better because the people who built them got better, and because the understanding of what could go wrong deepened with each generation of instrument. But the principle, the atom, the microwave, the feedback, the count, is the same as it was in 1955. The same as it was when Louis Essen stood in his laboratory in Teddington and confirmed that the Cesium resonance was real and measurable and stable. He was right, and the measurement stands. And now the definition of the second rests on it. On that beam of atoms drifting through a cavity, flipping their electron orientation in response to a microwave frequency that nature has apparently decided should be exactly 9,092,631,770 Hz. That number was measured against the stars in the 1950s, written into the international definition of the second in 1967, and it has not changed since. Because it cannot change. It is not a convention that can be revised by consensus. It is a measurement of a physical fact. The stars that were used to calibrate it have moved by tiny amounts in the years since. The Earth beneath Teddington has shifted fractionally with the slow drift of tectonic plates. The laboratory itself has been reorganized and updated and expanded. Essen and Parry are no longer alive. But the Cesium hyperfine transition still resonates at 9,192,631,770 Hz, as it did on the day it was first measured, as it will on any day in any future when there are still Cesium atoms in the universe and someone to ask them the question. You might be feeling, just now, the particular quality of rest that comes when something complicated resolves into something clear. It often happens in the middle of the night, when the thinking part of the mind loosens its grip and the larger picture becomes easier to hold. The Cesium clock is, at its heart, a simple idea. You ask an atom a question. The atom answers. You keep asking. And the answers, counted carefully, are time. But there is a question hiding under this picture. A question that the clock raises by its very existence. And it is a question that was not fully answered in 1967 when the definition was changed. It is a question that is still being answered now in laboratories far more sophisticated than the one in Teddington, with instruments far more precise than anything Essen and Parry could have imagined. The question is, how precise is precise enough? Because precision is not a destination, it is a direction. And in the direction of greater precision, extraordinary things have been found, things that make the Cesium beam clock look almost quaint, things that require an entirely new kind of clock, built on principles that were not even theoretical possibilities in 1955. Things that have made relativity, the abstract, philosophical, supposedly distant relativity of Einstein, into a practical engineering problem. But that story requires a cold room in Colorado and atoms slowed to within a whisper of absolute zero, and a technology that did not exist until the 1990s. So let that wait just a little longer. For now, rest in this somewhere on Earth, in several places. In fact, there are rooms where cesium atoms are drifting in beams, passing through microwave cavities, flipping their electron orientations, being counted. The clocks in those rooms are the legal definition of the second. They are what your phone and the satellites above you. And every radio-controlled clock in every kitchen and bedroom and laboratory on Earth traces its time back to. The chain is real, and it is unbroken. Your alarm in the morning is, at some remove of calibration and signal, a direct consequence of what Louis Essen and Jack Parry built in Teddington in 1955. And if you can still hear the sound of the city outside, or if the room you are in has that particular nighttime quiet where you can almost hear your own breathing, know that the count is continuing. The atoms are flipping. The oscillators are being corrected. The second is being measured and confirmed and handed forward into the next second, and the next, and the next. It has not stopped since 1955. It will not stop while you sleep. And yet, even as the beam clocks were humming in their quiet rooms, the people who built them knew there was a problem. A deep, structural problem. Not a flaw, exactly, more like a ceiling. The cesium beam clock worked by measuring how many atoms out of a given sample had flipped their electron orientation when the microwave swept through. The longer you could interrogate each atom, the more time each atom spent in the presence of the microwave field, the more precisely you could read the resonance. Ramsey's two-zone method had already pushed this further than anyone had managed with a single cavity. But atoms in a horizontal beam are moving fast. Even slowed by the state selectors and the careful geometry of the machine, they are still traveling at hundreds of meters per second. They pass through the cavity and they are gone. You get a fraction of a second with each one, and then it disappears into the detector. What if you could hold them still? Not perfectly still, not literally frozen in space, which is not a thing physics allows, but slowed. Slowed to a crawl, to a drift, to something approaching the temperature of empty space, cold enough that their motion becomes almost imperceptible. And the interrogation time stretches from a fraction of a second to something much, much longer. This was the idea behind the cesium fountain, and to understand it, you first have to understand what it took to even attempt it. In the late 1980s and into the 1990s, 3 physicists were doing something that sounded impossible. They were using beams of laser light, not to heat atoms, which is what you might expect light to do, but to cool them, to slow them down. The 3 were Stephen Chu, Claude Cohen-Tanuji, and William Phillips, working independently and then in concert, and what they figured out was this: if you shine a laser at an atom from the right direction, at exactly the right frequency, you can use the momentum of individual photons to act as a kind of friction. Each photon that the atom absorbs slows it just a tiny bit. Do this from 6 directions at once, left and right, up and down, front and back, and you surround the atom in what physicists started calling optical molasses. A treacle of laser light that resists motion in every direction. The atoms slow. They cool. They drift. They form in the right apparatus a small, soft cloud hovering almost weightlessly in the overlap of the laser beams. The temperatures they reached were extraordinary. Not just cold in the way a winter night is cold, temperatures measured in millionths of a degree above absolute zero. Temperatures colder than anything that occurs naturally anywhere in the observable universe. The coldest places in the known cosmos are inside physics laboratories. Chu, Koen-Tanuji, and Phillips shared the Nobel Prize in Physics in 1997 for this work. And the clocks that came out of it represent a different class of measurement from everything that came before. Here is what a fountain clock does. The laser cooling prepares a small ball of cesium atoms, hovering, barely moving. Then, and this is the part that is almost whimsical when you picture it, the ball is gently thrown upward. Just tossed, softly, like a child tossing a ball into the air in a garden. The ball of atoms rises through the microwave cavity, slowing as gravity pulls it back, then stops, and falls, passing back down through the same cavity on its way down. Two passes through the same field. The atom experiences the interrogation twice, once on the way up, once on the way down, and the total time it spends being questioned by the microwave is measured not in milliseconds, but in nearly a full second, sometimes longer. That extra time sharpens everything. The resonance peak narrows. The frequency measurement becomes more precise. The clock gets better. This is the cesium fountain. And in Boulder, Colorado, in a building that looks from the outside like any other mid-sized research facility, tucked into the foothills of the Rocky Mountains, the National Institute of Standards and Technology, NIST, built one. NIST F1 became a U.S. primary frequency standard in 1999. It was, at the time, the most accurate clock the United States had ever operated. It would neither gain nor lose a second in something like 20 million years, which is already a number that defies ordinary language. 20 million years ago, the continents were recognizably themselves, but the Himalayas were still rising, and the animals walking the earth bore almost no resemblance to the ones alive today. And then came NIST F2. NIST F2 was unveiled in 2014. It is a cryogenic fountain, meaning the whole apparatus is cooled to reduce the thermal noise that even the walls of the vacuum chamber can introduce. The result is a clock that would neither gain nor lose a second in roughly 300 million years. 300 million years ago, the first forests were just forming on Earth. The first amphibians were crawling out of ancient seas. The continents were still assembled in configurations nothing like the maps you know. Let that settle in, if you like. There is no rush. 300 million years of accuracy sitting quietly in Colorado, being checked and corrected and used as the reference against which other clocks are measured. The count continues. The second is being held. But even NIST F2, extraordinary as it is, was becoming a kind of forerunner. Because while the fountain clocks were being refined, another line of thinking was advancing, and it pointed towards something even stranger and more precise. Something that required the researchers to think not just about microwave frequencies, but about light itself. A microwave photon, the kind that drives a cesium fountain, oscillates about 9.2 billion times per second. That is an incomprehensibly large number by any everyday standard. But an optical photon, a particle of visible or near-visible light, oscillates hundreds of trillions of times per second. Somewhere between 300 trillion and 1,000 trillion, depending on the color. And if you could use a transition at optical frequencies as the tick of your clock, you would have 100,000 times more ticks per second to count, 100,000 times more opportunities to make a fine division. The potential precision is staggering. The problem for most of the 20th century was that you could not count optical oscillations. They were simply too fast. There was no gear train, no electronic chain, no technology that could bridge between a few billion oscillations per second, the rate at which existing electronics could follow, and hundreds of trillions. The frequencies were real, the transitions were sharp, the idea was right, but the counting was impossible. Until it wasn't. The solution came in the form of a device called the optical frequency comb, and the two physicists who developed it, John Hall working at Gila, the Joint Institute of NIST and the University of Colorado in Boulder, and Theodor Nusch at the Ludwig Maximilian University and the Max Planck Institute in Munich, shared the Nobel Prize in Physics in 2005 for making it real. The frequency comb works like this. Imagine a very short, very regular pulse of laser light, not a continuous beam, but a burst, a brief, precise flash, repeated at a very stable rate, perhaps 1 billion times per second. Now, a short pulse of light, by the mathematics of waves, is not a single pure frequency. It is a mixture of many frequencies, all bunched together. And when the pulse is regular enough, those frequencies arrange themselves into an extraordinary pattern, a series of sharp, evenly spaced peaks stretching across a wide range of the spectrum, like the teeth of a comb. Hence the name. Each tooth of the comb is a known, precise frequency. The spacing between the teeth is determined by the pulse rate, which can be measured with existing electronics. And so the comb acts as a ladder of known frequencies spanning from the microwave range all the way up into the optical. If you have a sharp optical transition in an atom or ion that you want to measure, you shine the comb at it and see which tooth aligns. You find the tooth, you know the spacing, and you can read the optical frequency in terms of countable lower frequency oscillations. The uncountable becomes countable. The too fast becomes measured. The frequency comb is, in a real sense, the gear train that the 20th century was missing. The mechanical clockmakers had gear trains to convert the fast swing of a balance wheel into the slow turn of the minute hand. The frequency comb does the same thing for light, translating the incomprehensibly rapid oscillations of an atom's optical transition into a signal that electronic counters can follow and record, and with it, the optical clock became possible. In Boulder, at Gila, a physicist named Jun Ye has spent years building what are now among the most precise clocks on Earth. His approach uses strontium, not cesium but strontium, chosen because it has a particularly useful and extraordinarily narrow transition at an optical frequency. The atoms are held not in a beam, not in a fountain, but in a lattice of laser light. You can think of the lattice as an egg carton made of light, with each hollow a tiny trap, and in each trap a single strontium atom, held almost perfectly still, cooled, isolated from interference, ready to be interrogated. Thousands of atoms are trapped at once, and they are all read simultaneously, which gives a statistical advantage. More atoms, less uncertainty. The strontium optical lattice clock that Jun Ye's group has developed reaches fractional uncertainties around 10 to the power of -18. 10 to the -18. The number is almost absurd to say out loud, so let me try to translate it. At that precision, the clock would neither gain nor lose a second in a span of time comparable to the current age of the universe. The universe is roughly 14 billion years old. A clock at 10 to the -18 would still be accurate if it had been running since the Big Bang, and you checked it now. There is no earthly phenomenon you could use to verify that across such a span. The comparison is a mathematical consequence, not a practical test. but it tells you something real about where the edge of measurement now sits. And here is where the story turns, quietly, into something that touches you. Because the optical clocks got so good, so exquisitely, almost unnervingly precise, that they started to notice something. Something that in an earlier era you would have needed enormous machines and very long experiments to see at all. Something that Albert Einstein had predicted in 1915 and that had always felt like it belonged in a different universe from the one where people buy groceries and check their phone for directions. They started to notice that height matters. General relativity, Einstein's theory of gravity, makes a specific, testable, mathematical prediction. It says that a clock lower in a gravitational field, closer to the mass of the Earth, will tick slightly slower than a clock higher up. The gravity pulls on time itself. A clock in a basement ticks slower than a clock on the roof. A clock at sea level ticks slower than a clock on a mountain. Not by much, not by anything a human body could feel, but by a real and calculable amount. The deeper you sit in the gravity well, the more slowly your local time runs. This is gravitational time dilation. It is one of the cleanest predictions of general relativity, and it had been tested before. In 1971, two physicists named Joseph Haffel and Richard Keating did something beautifully simple and also faintly absurd. They put cesium atomic clocks in the passenger compartments of commercial airliners and flew them around the world. One set of flights went eastward, one westward. The airborne clocks experienced both the time-slowing effect of their speed relative to the ground. Special relativity, the faster you move through space, the slower your clock, and the time-speeding effect of being higher up in weaker gravity, further from Earth's mass, general relativity. When the clocks landed and were compared to stationary reference clocks, both effects were there, exactly as predicted. The numbers were small, tens to perhaps 100 or so nanoseconds. But they were real. They matched Einstein's equations. Time dilation was not a theoretical possibility. It was a thing you could measure with a cesium clock on a commercial flight. But here is how far the technology has come since 1971. In 2010, a team at NIST, Chin-Wen Cho, David Hume, Till Rosenband, and David Wineland, used optical clocks built around single aluminium ions to measure gravitational time dilation not across the altitude difference of an airliner flight, not across the height of a mountain, but across a height difference of 33 centimeters. 33 centimeters. About 1 foot. The height of a single curb. They raised one clock by 33 centimeters above the other and measured the rate difference. And they found it. The higher clock ticked faster by a small but unambiguous and measurable amount. The general theory of relativity, the same theory that describes the bending of starlight around the sun, the same theory used to model the structure of the universe, was demonstrated in a laboratory across a distance you could step over without thinking. They also measured time dilation from motion. They oscillated one of the clocks at a walking speed, around 10 meters per second, and measured the tiny slowing of its tick rate due to special relativity. A clock moving at walking pace runs measurably slower than one sitting still. Not by much, not by anything a human life could accumulate into a meaningful difference, but measurably. Precisely, unambiguously, relativity at this point is not a distant or exotic thing. It is a calibration problem. It is an engineering correction. It is something the people who build and maintain the most precise timekeeping systems on Earth think about the way an aircraft mechanic thinks about metal fatigue, not as philosophy, but as a practical reality that has to be accounted for. And nowhere is this more concrete or more quietly consequential for your daily life than in the satellites circling the Earth right now. The Global Positioning System, GPS, depends on a very simple idea. If you know exactly when a signal left a satellite, and you know exactly when it arrived at your receiver, you can calculate the distance, because the signal travels at the speed of light, and the speed of light is fixed. Do this with signals from 4 or more satellites, triangulate, and you know where you are. The precision of the whole system rests entirely on the precision of the clocks. A nanosecond of error in the clock becomes about 30 centimeters of error in your position. A microsecond becomes about 300 meters. The clocks aboard GPS satellites are atomic clocks, and they have to be right. But here is the problem. The satellites are moving very fast, about 14,000 kilometers per hour, roughly 4 kilometers every second. Special relativity says that a moving clock runs slow. The satellite clocks, because of their speed, fall behind ground clocks by about 7 microseconds per day. At the same time, the satellites are orbiting at an altitude of roughly 20,000 kilometers, far above the Earth's surface, and therefore in weaker gravity. General relativity says that a clock higher in the gravity well runs fast. The satellite clocks, because of their altitude, run ahead of ground clocks by about 45 microseconds per day. These two effects pull in opposite directions. Speed slows the clock, altitude speeds it up. The net result is that GPS satellite clocks run faster than ground clocks by approximately 38 microseconds per day. Not slower, faster, 38 microseconds per day. That number does not sound large. But if you let it accumulate uncorrected, if you simply put the clocks in the satellites and left them alone, pretending Einstein had never existed, the position error in GPS would grow by roughly 10 kilometers per day. Within a week, the system would be useless for navigation. Within a month, your phone would be placing you in the wrong city. The engineers who designed GPS knew this. Before the first satellites were launched, the clocks were deliberately set to run at a rate slightly slower than their design frequency, so that once they reached orbit, where gravity is weaker and they would naturally speed up, the correction would bring them back to the right rate, relative to ground clocks. The relativistic correction is baked into the design of the hardware, not applied after the fact. Every GPS satellite that has ever been launched carries, built into its clock hardware, a direct acknowledgement that Einstein was right. And the time reference that GPS traces back to, the master signal, the authoritative source, is maintained by the U.S. Naval Observatory in Washington, D.C. The Usno master clock is an ensemble of cesium beam clocks and hydrogen maser clocks, all running together, averaged and corrected and watched over continuously. The USNO provides the time reference for GPS and for much of the United States Department of Defense's timekeeping infrastructure. The chain that runs from a cesium atom's hyperfine transition to the blue dot on your phone's map runs through this ensemble. Through these quiet rooms of humming hardware, through decades of careful calibration. Your navigation, in other words, is built on quantum mechanics, general relativity, and the work of men and women who spent careers counting atomic oscillations in basements. It has been since the GPS constellation first became operational. You just may not have known. And the optical clocks have introduced a new possibility beyond GPS. Because they are so precise, because they can detect the fractional frequency difference caused by a height change of a single centimeter, they can be used as sensors of the Earth's gravitational field. If you place two optical clocks at different locations and compare their tick rates, the difference tells you something about the difference in gravitational potential between those locations, which is connected to the altitude and the local density of the rock beneath your feet. This technique is called relativistic geodesy, using clocks to measure the shape and gravity of the Earth itself. Surveyors once used theodolites and spirit levels. The next generation may use atomic clocks, comparing tick rates down fiber optic cables to map the planet's gravity with an accuracy no previous technology could approach. Time, which began this story as the count of swinging pendulums and the position of the sun, has become a tool for measuring the planet. But there is one last wrinkle, one last place where the tension between the atom and the Earth surfaces visibly and practically. It is the leap second, and its story is, in a way, the cleanest summary of everything this history has been building toward. When the 13th General Conference on Weights and Measures redefined the second in 1967, humanity made a choice. The atom is the master. The second is not a slice of the Earth's rotation, it is a fixed count of cesium oscillations. But there was a practical problem. Timekeeping systems around the world, radio broadcasts, naval navigation, civil infrastructure, had been built around the assumption that the clock and the sky were in approximate agreement. The sun should be at its highest point in the sky at something close to noon on your clock. If the atomic second drifted away from the astronomical second indefinitely, eventually noon would arrive at 1 in the morning. That would be confusing. The solution was Coordinated Universal Time, UTC runs on atomic time, using the SI second defined by cesium. But it is periodically corrected to stay within 0.9 seconds of UT1, which is the timescale based on the actual rotation of the Earth. The correction is applied by inserting a leap second, an extra second added to the clock, like a patch, to keep the civil timescale in rough agreement with the sky. The first leap second was added on the 30th of June, 1972. Since then, through the end of 2016, 27 leap seconds have been inserted, always on the 30th of June or the 31st of December. Always announced about 6 months in advance by the International Earth Rotation and Reference Systems Service, which monitors the Earth's rotation and decides when a correction is needed. 27 extra seconds in roughly 45 years. It sounds like a small thing. And in human terms, in terms of the lived experience of a day or a year, it is a small thing. The extra second passes, and you barely notice, and then it is over. But in terms of the systems that modern civilization runs on, the computers, the financial networks, the telecommunications infrastructure, the servers that coordinate global internet traffic, a leap second is a significant and somewhat dangerous event. On the 30th of June 2012, when a positive leap second was inserted, several major internet services failed. The reason was that the software running those services had not been designed to handle a minute that contained 61 seconds rather than 60. Clocks rolled from 23:59:59 to 23:59:60 to 0 ROM. And systems that expected the minute to end at 23:59:59 became confused, locked up, or crashed. Reddit, LinkedIn, and a number of other large services experienced significant outages. It was not catastrophic, but it illustrated the problem. The leap second, an elegant compromise invented in the 1970s, had become a source of real risk in a world where global computing infrastructure depends on continuous, uninterrupted, perfectly consistent timekeeping. The timing of each leap second is unpredictable. You cannot, in advance, know exactly when the Earth's rotation will slow enough to require another correction. The announcement comes roughly 6 months before the event, which is not enough time for many large systems to test and deploy changes. And the Earth, as we have already established, is an unreliable witness. Its rotation varies in ways that cannot be forecast years ahead. There is no clean formula. There is only the monitoring and the announcement and the scramble. By the 2010s, a serious argument had developed within the international timekeeping community over whether the leap second should simply be abolished. Let UTC run on pure atomic time. Let the divergence between UTC and UT1 accumulate, with no correction applied, until the difference becomes large enough to matter, and then, perhaps, apply a much larger correction, a leap minute or a leap hour, scheduled far in advance. Future generations could deal with the sky. The present needed stability. The debate ran for years. It was not simple. Some communities, astronomers, satellite operators, certain military systems depended on OTC being close to UT1. Others, most of global computing infrastructure, found the leap second's unpredictability intolerable. In November 2022, the 26th General Conference on Weights and Measures, the same body that had redefined the second in 1967, adopted Resolution 4. The leap second would be abolished, or at least suspended, by or before 2035. The allowed divergence between UTC and UT1 would be increased significantly, the exact new tolerance to be determined, but large enough that corrections would be very rare and could be scheduled far in advance. The details are still being worked out. But the direction is clear. By 2035, we will have officially and formally decided that the atom is right and the Earth is the thing that is wrong. Not metaphorically, not philosophically, in the official, legal, internationally agreed definition of time. The planet that gave us the second, the rotation that human civilizations counted for thousands of years, will be the anomaly to be corrected, and corrected rarely. On a schedule convenient to us, not on a schedule imposed by the unpredictable wobble of a rock in space. That is where the arc ends. That is where the line that runs from Huygens pendulum in 1656 to the Cesium fountains in Boulder in 2014 arrives. We asked the sky what time it was for all of recorded history, and then we stopped. And now we are choosing, deliberately, to ask less often. So let's travel back, for just a moment, to the beginning of this journey, to the image that opened it. A clock is being raised, just slightly, 33 centimeters, the height of a step. The NIST team in 2010, with their aluminium-ion optical clocks, performing an experiment that would have been impossible in any previous decade. The clock rises, and it runs faster. Not because anything is broken, not because of any imperfection in the machinery, but because the universe itself is structured so that time passes at different rates in different places, and now we can feel it. Now we can measure it across a distance smaller than the arm of a chair. You are lying down right now, or nearly so. Your head is probably slightly higher than your feet, which means, in the most precise accounting the universe makes, time is ticking at a fractionally different rate at the crown of your skull than at the soles of your feet. The difference is immeasurably small for the clocks we carry around in our bodies and our daily lives. No alarm will ever go off early because of it. No appointment will ever be missed. But it is real. The universe computes it continuously. You are, at this very moment, a tiny gravitational gradient. Your blood flows uphill and downhill. Your neurons fire at the top and the bottom of a gravity well. Einstein's equations describe you without apology or abstraction. And the cesium atoms, the ones in Boulder and in the other national laboratories around the world that maintain primary frequency standards, are flipping their electron orientations right now, as you breathe. As whatever light is left in your room settles into the dimness of the late hour. As the city outside, if there is one, quiets toward its most hushed. As the house, if you are in one, makes its small, settling sounds. The count continues. The second is being measured and confirmed and handed forward, as it has been without interruption since Louis Essen and Jack Parry switched on their apparatus in Teddington in 1955. You are not separate from that count. The phone near your bed or on its charger across the room, the one that will tell you the time when you wake, keeps its time by synchronizing to a network that traces back to the fountain clocks in Boulder and to the Usno master clock, and to the international comparison of primary standards around the world. The number those clocks agree on propagates outward through fibre and radio and satellite signal into every connected device on Earth, into the GP's satellites above you, whose clocks are running fast by 38 microseconds a day and have been corrected for that since before launch, into the infrastructure that moves money and coordinates aircraft and keeps the Internet's timestamps consistent. All of it, the whole vast coordination of modern time, reaches back to a resonance inside an atom. A specific resonance. A specific atom. One whose properties are not an accident of where it was found or how it was made, but a fixed and universal feature of matter itself. Identical here and on the far side of the galaxy, identical now and in 300 million years, identical in every laboratory and every star system where cesium exists. That was Rabi's insight in 1945. That was what made the atomic clock not merely more accurate than what came before, but different in kind. Every previous clock was a human artifact, subject to the imperfections of the material it was made from and the world it sat in. The cesium standard is not an artifact, it is a fact about the universe. The number 9,192,631,770 was not chosen. It was discovered. It was the resonance that was already there, waiting to be counted. And in 1967 the world agreed. A second is 9,192,670 of those resonances. Not because a committee decided it should be, not because it was convenient, but because the atom was more reliable than the planet, and reliability is what time requires. We stopped asking the Earth what time it was. We stopped trusting the spinning world beneath us, and the clocks we built instead got good enough to feel the height of a single step. That, in the end, is the whole story. From the pendulum swinging in Christian Huygens' workshop in the winter of 1656 to the atoms drifting upward through the microwave cavity in a cold room in Colorado. From the sailor trying to find his longitude somewhere in the middle of the Atlantic, holding John Harrison's chronometer and watching for noon, to the strontium atoms held motionless in a lattice of laser light while the frequency comb counts their oscillations at 400 trillion per second. From the second as a fraction of a day, a slice of a planet's rotation assumed to be reliable, proven not to be, to the second as a property of matter itself, fixed and universal, against which the spinning world must be corrected. It is, when you sit with it, a remarkable reversal. For thousands of years, the sky was the clock, the sun, the moon, the stars. They were the standard, and human devices were the imperfect instruments that tried to keep up. Now the instruments have surpassed the sky. Now the sky is the thing that drifts. Now we insert a leap second, not because the atom is wrong, but because the Earth is. And by 2035, we will not even bother to do that very often. The planet is still here, of course, still vast and warm and spinning, still the thing you are lying on right now. It's gravity pulling you softly downward into whatever surface you are resting on, holding you in place. That gravity is the same force that makes the clock in Boulder tick at a different rate from the clock at Gila a few floors higher. The same force that makes your feet tick ever so slightly slower than your head. The same force that Haffley and Keating put into their suitcases on commercial flights in 1971 and came back with measured, confirmed, unambiguous results. The planet is not a bad clock in every sense. It is a beautiful, ancient, complicated world, and the human relationship with its rhythms runs deep in the body and in the culture, in the language of days and months and years and seasons. We will not stop watching the sky. We will not stop knowing that the sun rises and the sun sets, and that these things matter. We will simply have stopped pretending that the sky is precise. We know better now. And you know better now too. You have come a long way tonight. From pendulums to chronometers to vibrating crystals to laser-cooled atoms in a boulder fountain to strontium held in a lattice of light, while the frequency comb bridges the uncountable to the countable. You have followed the resonance from a swinging weight in a Dutch workshop to the hyperfine flip of an electron in an atom so cold it barely moves. You have traced the second from a fraction of a day to a fixed count that will not change, anywhere, ever, and somewhere in it, if you are still awake enough to feel it, there might be a small, quiet satisfaction in the knowledge that the strangest prediction of relativity is not a thing that happens in black holes or at the edge of the universe. It happens in a room in Colorado. It happens across a steppe. It happens in some infinitesimal and uncountable way inside the small gravitational gradient that is your body right now in the quiet of wherever you are. You are of it, all of it. The oscillation, the count, the calibration. You are a physical system in a gravitational field, and time passes through you at the rate the universe decrees, and somewhere in Boulder the second is being confirmed and handed forward. If you enjoyed this slow journey through time itself, a like and a subscribe would mean a great deal. Small creators like me rely on your support to keep these nights going. And wherever you are in the world tonight, whatever time it is in your corner of the dark, thank you for being here. Thank you for traveling all this way. Sleep well, fellow voyager. The next journey keeps until you wake.